Recording started. So we discussed the rational formula, and I ended the last lecture by saying that you should remember the definition of time of concentration, and you should remember the definition of return period. Okay. And then about the rational formula, let me make a final consideration. We mentioned some assumptions of the rational formula, and basically we mentioned that we assume that the return period of rainfall is the same as the return period of the computed river flow. This is the first assumption, and you see it's here. When applying the rational formula, one usually assumes that the return period of rainfall and the consequent river flow are the same. And then it is written here, further explicit assumption and implicit assumption of the rational formula are not discussed here. Okay, so I just want to say that there are other assumptions underlying the use of this formula, which we don't discuss here. And it's just enough if you want to look at them, look on the web, and there is plenty of information. I just want you, please, to remember, because you may get a question in the quiz like, what are the assumptions that we discussed of the rational formula, something like that. So equality of the return period, and another thing that I ask you to remember is this one. As for the duration of the rainfall event, it can be proved under certain assumptions, which we don't discuss, that the rainfall duration that causes the most severe response by the catchment in terms of peak flow is equivalent to the time of concentration. And I asked you to remember definition of time of concentration, which is given here. Okay. Okay, just take note of these things to remember. One thing I want to say for the exam may be that I already said that. So, as I said, it is composed by a quiz plus a short oral. In some cases, I may decide to skip the oral to give you this opportunity if you want. Okay, like, okay, you got a mark in the quiz of 30. Would you like to take the oral or not in order to maybe try to get the laude or whatever? Or you take 30 and you leave the room and you go home already now? Sometimes it may happen. This is a decision that I take by considering several type of information. It's not given for granted, so please don't assume that you always have the opportunity to skip the oral. So I just wanted to tell you that there might be this opportunity, and which I give to you. It depends on several information that I consider. For instance, because you may be curious, the composition of the quiz is random, and the quiz is different for all the students in the room. So if I see that the students got, by chance, a combination of questions that are characterized by being tough, then I may think, oh, the student was particularly unlucky, but still, he answered all the questions well, and I may give the opportunity. Okay. This is one of the things that I consider. So don't take it for granted, because I say this because last year I had some students saying, the other guy got this opportunity, so I want also for myself to get it. And I said, sorry. So I want to make it clear. Okay, perfect. Okay, let me move forward with another model. Remember, we are talking about rainfall runoff modeling, and rainfall runoff modeling is related to assessment of climate change impact, because as I said, usually we get a prediction by climate models, which is not of river flow, it's rainfall, a prediction of rainfall in future climate. There is the last generation of models that is also providing a proxy for river flow. So the last generation of models also try to compute the river flow. It's not really computation of river flow, it's a proxy. What is the proxy? It's an estimate for each grid cell of the production of runoff and then you have to integrate over the considered catchment if you want to get it. So this information is anyway useful to you. So it's not strictly true that models, climate models, give only rainfall. The previous generation, yes, they gave only rainfall. The previous only temperature. They are refining their simulation, trying to provide additional variables. But usually, if you want to make a technical estimation of river flow, it is advisable that you don't take directly the runoff simulation from the climate model, but you take the simulation of rainfall and use a rainfall runoff model. Why? Because the rainfall runoff model is less uncertain than a climate model. The rainfall runoff model is a local model. It is applied at local scale. It uses a lot of local information. The climate model is a global model, so you understand the difference. If it is a global model, it cannot really be very precise at the local level. So usually it is advisable that, you use the specific models. And I want to exaggerate. If you had a climate model in the future estimating the wind pressure over a building from the climate model, I wouldn't suggest that you take the estimate from the climate model. I would suggest that you use a model of structural engineering that, based on the wind velocity given by the climate model, computes the stress over the particular structure of the building by taking into consideration the structure, the internal structure of the building. Same here. You have a lot of information about catchments that is not considered by climate models because they need to work at the global level. And therefore, it is anyway advisable that you use these rainfall runoff models in order to estimate the hydrological impact of climate change. So the rational formula is a very simple model. It's clear that it has limitations. So what are other models, more complicated models that we could consider without making it too complicated? I want to mention a model that is widely used, especially for computing the discharge of drainage canals from flat regions. Like, for instance, here we have irrigation consortiums that are also here in this region, in this huge flat area, the only large flat area that we have in Italy. We have consortiums taking care of drainage and irrigation by managing canals. And you understand that the management of drainage in flat areas is much different from the management of drainage in mountains. You have to use different models. And the linear reservoir is especially used to compute the river flow in flat areas. Why in flat areas? Because it is based on the concept of storage. It takes into account the storage in a basin. And the storage is higher in flat areas than in rapid hill slopes, rapid, I'm not sure it is English, steep hill slopes, okay? And because the Italian translation of steep is ripido, so maybe it's also an English term, but I'm not sure, so let me say steep, okay? And so if the storage is important, then the idea is to assimilate the catchment to a reservoir. Reservoir, of course, storage is important. And look, the rational formula doesn't consider storage. This is one of the reasons you see here. Okay, you may say that it's implicitly considered by the runoff coefficient. True. But it's not explicitly considered. And changes in storage are not considered here in the rational formula. It is just a proportion of rainfall. We assume that a proportion of rainfall is translated into river flow. So if we want to consider the dynamic evolution of storage, a good idea could be that we assimilate the catchment to a reservoir, like a dam, an artificial reservoir, where we have rainfall entering into this reservoir, only rainfall, and then we have an outflow, okay? The linear reservoir is a model that is widely used because it's very simple. This model is old, it's an old model, has a long history of applications, and simplicity was the target at that time. I mean, the linear reservoir goes back to beginning of the 20th century. The rational formula goes back to 1859. The linear reservoir, I would say that probably the basis were drawn beginning of 1900. And at that time, the target was simplicity because they didn't have computers. They needed to make a manual computation. And so the idea is also to make the model linear. And because linearity, it implies also simplicity of the computation, okay? So if we assimilate the catchment to a reservoir, let me just make a sketch over the blackboard. And let me just see if the camera, I need to change the camera, 1 second. Okay, here it is. Let me just, okay, so I think, let me see. Okay, this is the blackboard. Let me make a sketch here. Because the idea is very, is brilliant. It's simple and brilliant. So let's assimilate the catchment to a tank. So let me take a white chalk because let's assimilate the catchment to a tank where I get rainfall in. Rainfall is depending on time. Let me see. Let me just change the orientation of the camera and also, okay, I think in that way it should be visible. We get rainfall in and we get the river flow out from the bottom discharge QT. It's dynamic, but here I have a storage. You understand that when it is empty, I start getting rainfall and I don't get any outflow. But then after a while, I get a storage here, WT. And then the storage causes the formation of a bottom discharge, okay? And the linear reservoir assumes this very simple structure, and it assumes that there is no limitation to storage. So WT can increase forever, okay? And of course, there is a limitation, a bottom limit to 0. And then, in this case, I can apply in a very simple way the continuity equation. So I can write that the change of storage along time is equal to rainfall minus outflow. One important thing, this is actually because we have to specify what we mean for rainfall. Okay, rainfall is actually should be expressed here as volume per unit time of rainwater over the catchment. So it's not rainfall intensity, it's volume per unit time. So if we indicate the rainfall intensity, which we considered before with the symbol I, and rainfall intensity is defined in terms of units as a length divided by time. Length because it's a rainfall depth. So it is like I measure the depth of rainfall in 1 hour, and then depth divided by time, 1 hour, gives to me the intensity. Is it clear? So it's depth divided by time. If I want to get the rainfall P, which I need to introduce here, this is given by the intensity times the area. This is PT. PT is rainfall intensity times the area. Yeah, everything is written over the blackboard. Perfect. And is visible there. So let's be clear, because otherwise you see that here I am taking the difference between rainfall and river flow. It means that the units must be the same. River flow, we know that it's length cube divided by time. As we defined it, river flow is like cubic meters per second, length cube divided by time. So also PT must have the same unit. And in fact, here you see length divided by time, rainfall intensity, times the area of the catchment, length square, and you get, again, length cube divided by time, which is fine. Everything is clear about this? No questions? Okay. So this is a continuity equation, is a mass balance equation. And you see that it's a differential equation because we already discussed this. When we apply conservation equations, very often we need to write them in differential form. And this is a differential equation. But it is very simple, you understand. The change in storage is equal to the difference between rainfall minus river flow. It's very clear. Now, and I mean, the idea is brilliant. It's brilliant. It's very simple. And it is brilliant because it works, indeed. We can prove that it works. Let me just put here. Okay. You see on the screen, I put the same equation over there. Yeah, there is the difference. Sorry that it's lowercase there, PT and QT, and here is uppercase, but okay. It's don't look at the very tiny details. You know that you have to study there, okay? And but there is a but here. Can we solve this equation alone? First, you should think that it would be strange that only with a conservation of mass you can describe an hydrograph. It would be strange because you understand that only mass conservation, it's not enough. You should introduce also, given that you describe something dynamically river flow and evolving in time, you should introduce a conservation of energy or something that gives to you a kinematic interpretation. Okay, so interpretation of river flow velocity. Velocity means conservation of energy, not only conservation of mass. So you understand that there is something missing here, okay? And indeed, also in the rational formula, there is something missing. So, I mean, but if you look at this equation, you understand that the only known variable here is precipitation. Storage is unknown and river flow is unknown. River flow is our unknown. But also storage, which I introduced because I want to account for it. Even if I'm not directly interested in storage, I want to account for storage. And I introduced this variable, which is not an output variable, it's not an input variable, it's a state variable. It's a variable that describes the state of the system, the storage, like the state of the system in the Romagna region when the second flood occurred. What was the storage? Okay. So basically, then we have to introduce the second equation. And the second equation, if I want to describe, I mean, it should be an equation that either gives to me an explicit value for the state variable or the river flow, like I have a measurements of storage. This is impossible, but let's suppose that I have measurement of storage. So either I add a second equation giving to me an explicit representation for storage, or I can add a second equation that gives a relationship between storage and river flow, the two unknowns. Okay. So what is an equation that may explain the relationship between storage and river flow, conservation of energy. If you remember when you had your basic of hydraulics and fluid mechanics. This is the word that I was looking for. You may remember that the relationship between storage and river flow, for instance, in a tank, in a reservoir, is a conservation of energy. You can obtain it through a conservation of energy. So the relationship between the storage and the bottom flow from a reservoir, for instance, is a conservation of energy. So it means that here I should add a conservation of energy equation. But if I want to simplify things, it is just enough that I introduce a relationship between W and Q. If I want to simplify things, okay, I may say, okay, conservation of energy may be a solution, but I want something very simple. So I can introduce an empirical relationship. And the idea is indeed very simple. The idea is to introduce a relationship, a linear relationship between WT and the river flow. So WT is given by a constant times QT. And this constant has the unit of if you remember what we discussed before, cubic length divided by time, storage, volume, cubic length. So this is time. Okay. And this is what you see there. This is a brilliant idea because it is an emulation of conservation of energy. And it is brilliant because if K is constant, the relationship is linear. And we can prove that it makes the whole relationship between river flow and rainfall linear. So it's brilliant. It's brilliant because linear means very simple. And then now we can solve this system of equations. And let me see. Yeah, there is the solution here. So it is easy to solve it, and up to a certain extent, because I'm now showing how we can solve it. I think in 5 minutes I can more or less get there. The first thing that we have to do is to put together the two equations. Okay, so I can substitute here so the T of KQT is equal to 15 minus QT. You see that we eliminated storage from there, so storage is no more here. It means that we have only an unknown here, is QT. And therefore, we can solve it. Of course, we need an integral. We need to compute an integral to solve it. But before computing an integral, let's write, this is a constant. I can take it out of the derivative. K, the Q over the T is equal to T minus QT. Okay? This is the first step. And then there is a trick here to integrate this equation. Now let's integrate it. There is a trick. The trick is to multiply both left and right hand sides by e to the power of p over k. Okay, so here you get k the t over the t is equal to e to the power of p over k pt minus e to the power of p over k qt. Let's see if we are still, yeah, it's still there, visible on the screen. Okay, so now that we made this multiplication, we can write it in this way. So basically, let's bring to the left-hand side the term with the q that is now in the right-hand side, okay? So let me rewrite this in this way. Let's rewrite this in this way. A to the power of t over k, k, the qt over the t, plus e to the power of t over k, qt. And this is equal to e to the power of t over k, dt. Okay? Good. Now, this term here is equal to this to the t of what? Of e to the power of t over k to t. Let me see if I did everything. Yes. And of course, the right-hand side is the same. Good. Now we can integrate these two terms. And, you know, the trick has been finalized to obtaining the derivative of a product here. It's very easy to compute the integral of a derivative, of course. The argument of the derivative becomes the integral. So let me compute it here. Let's compute the integral between the limit of integration. Let's put it between 0 and t. Okay, so let me write first the right-hand side, integral between 0 and t of e to the power of t over k dt. Okay, so you understand the extremes of integration between 0 and t. And here, the integral of the derivative is simply the argument of the derivative times qt computed between the extremes 0 and t. Everything is clear? Okay. Yeah, it is the same here. Perfect. One thing, the integral should be in the tau, and here this is tau, and here this is tau. Okay, variable of integration. So tau varies between 0 and t, and for changing tau, changing time, I need also to change here and here. Okay. And I think same here, sorry. Tau and tau. Now we can compute easily the first one. So now we have to put tau equal t, so substitute the upper limit into the variable of integration, and then we get e to the power of t over k q t minus, so now we have to put tau equals 0. So basically, if tau equals 0, we have minus q0. Because e to the power of 0 is 1, and this is minus q0. And this is equivalent to, here, let's keep it unchanged for clarity for now. E to the power of tau over k p tau, because I don't want to make many steps all in once. Okay. So now we have this one here. Good. We are at this step here. Yeah, I can't select it, but I put the mouse there. Or we are here, correct. Now let's assume that Q0 is 0. Okay, so let's assume Q0 is 0. We can remove this assumption, and we may also remove it later. And therefore, we can write this. So let's write here Qt is equal to, and in order to, I have to divide 1 minus divided by e to the power of t over k, because I divided both sides by e to the power of t over k. And this is, right-hand side is unchanged, e tau k e tau the tau. Oops, sorry. This is not an equal, but it's a multiplication. Good. And now this is a constant, you see, because k is a constant and t is a constant, is the limit of integration. So I can bring it, inside the integral, because it's a constant, I can't move it here. So I can rewrite this in this way, ut is equal to integral between 0 and t of e to the power of tau over k divided by e to the power of t over k, t tau in the tau. And now we are here. And then we can write, let me just take some room here. I think it's the last step. Qt is equal to integral between 0 and t of, okay, we can write this ratio in this way, e to the power of tau minus t divided by k, p tau in the tau. Okay, that's fine. And now we can write, okay, we can, let me just take another line free. Usually, we change a sign here and write it in this way, e to the power of minus t minus tau over k, t tau in the tau. Okay, And now I am missing a 1 over k. Where did I lose it? Do you have any suggestion? I missed the 1 over k. Yeah, okay. Because the final result is 1 over k here. I remember it by memory, so I forgot it somewhere. Okay. I'm sorry because I deleted it, but I think that you can easily correct. And I think it should be, let me see if it is correct here. I need to check because I'm not sure it is correct. Yeah, it is. Yeah. Here it is correct. Here is correct. I forgot on the website is correct. So follow the website, and here I forgot 1 over k. But this is the final relationship, and let me just conclude it by saying a couple of things. First of all, sorry if I took more of your time, but I just want to highlight this. Here you see still an integral, okay? You see still an integral because we don't have an explicit representation for rainfall. So what is the reason why I'm not moving forward and solving the integral? Because rainfall usually is given as a series of numbers. It's not an analytical relationship. So I can't move forward from here. This is why usually the linear reservoir is expressed through this equation. But this equation, the integral, as we said several times, is a summation. So you can understand from this that river flow is a linear function of rainfall. Is a linear function, okay? Because as time is progressing, you see that it is the multiplier of rainfall remains just related to time. So it's a linear function of it, okay? And second consideration, I said that we can't move forward with the integral, but if you assume that rainfall is constant, this can be easily integrated. And let me see if there is integration here. Yes, there is integration, but we will discuss it next time. The integration with the assumption of constant rainfall can be easily integrated and gives a river flow that is represented here. This is under constant rainfall, okay? And you see that basically under constant rainfall, you get asymptotic convergence of river flow to rainfall asymptotically. But of course, we are assuming here that rainfall is constant and lasting forever asymptotically. But we will discuss this graph and the integration under constant rainfall next time, okay? So I apologize once again for forgetting 1 over k somewhere here, but if you follow the website, you get the correct development. Thank you. See you next Monday.